All right. So it's a great honor to speak to you today at ICAO 2025 on the COLIEE workshop. I'm Takao Mizuno from Frame and collaborating with Professor Yoshinobu Kano, Shizuoka University. Today I will present our COLIEE 2025 submission titled Hierarchical and Referential Structure-Aware Retrieval for Statutory Article using Graph Neural Network. So let me start with a brief overview of today's talk. I'll begin with the background and challenges, then introduce our structure-aware retrieval methods, followed by experiment and discussions. And it's already been discussed, so I skipped the general introduction to COLIEE. In this talk, I focus on Task 3, Statutory Article Retrieval. In Task 3, the input is a legal question taken from the Japanese bar exam. The output is a set of civil code articles that are relevant to answering that question. The model is evaluated based on how well its predictions match the gold standard article set using macro averaged F2 score. Statutory article retrieval is particularly challenging in the context of Japanese law because legal texts are highly structured and context independent. Specifically, we face three main issues. First, hierarchical content independence. Second, implicit dependencies between articles. Third, explicit article differences. I explain each of these briefly in the following slides. First, a hierarchical context is essential when interpreting Japanese statutes. Articles appear at the bottom of the multi-level structure, including parts, chapters, sections, subsections, divisions, and captions. And in Japanese law, captions sometimes serve as shared headings that apply to multiple articles, so we treated them as separate structural nodes to correctly capture that scope. Capturing this hierarchy helps the model understand how specific article fits into the broader legal framework. Second, articles often depend on concept-defined nearby provisions, even if those links are not explicitly stated. For example, Article 89 uses the term natural foods, which is actually defined in Article 88. If we ignore these implicit dependencies, we may miss key provisions that are necessary for legal interpretation. Third, some articles explicitly refer to other provisions. For example, Article 291 refers to Article 166 and Article 219 refers to the preceding article. These references created clear semantic links across different parts of the law. So a retrieval system needs to capture these connections to fully understand the legal context. Before introducing our method, let me briefly review the standard retrieval approaches. Sparse methods like VM25 relies on lexical overlap and work well for exact matches. Dense bioencoders map queries and articles into vector space for semantic matching, and cross-encoders jointly encode the query and article, enabling fine-grained re-ranking. This bioencoder plus cross-encoder setup is commonly referred to as two-staged retrieval. Our methods build on these frameworks, but instead of treating the law as a flat collection of articles, we model its hierarchical architecture explicitly as a graph. Many retrieval models treat each article as isolated unit without considering its structural or contextual surroundings. But in legal texts, interpretation often depends on hierarchical headings, neighboring provisions, and cross-references to other articles. Ignoring these aspects can lead to retrieval errors, especially when legal meaning is distributed across multiple provisions. So Our goal is to design a retriever that reflects the structure of the law rather than treating article in isolation. To model legal structure, we focus on graph neural networks. A GNN operates on graph structured data and updates each node's representation by aggregating information from its neighbors through message passing. This process produces context-aware embeddings that reflect each node position in the structure. In our case, nodes represent articles or structural headings, and edges represent containment relationships like part, chapter, and article. This helps model incorporate structural context into RT representations. So our proposed method, JLGR, Japanese Legal Graph Retriever, incorporates the graph neural networks to encode the hierarchical structure of law. It models articles and structural headings as nodes in the graph, enabling structure-aware representation learning. Also, to leverage recent advantage in retrieval accuracy, JLGR adopts a modern two-stage architecture. First, graph-augmented bioencoder retrieves candidates' articles, and then a cross-encoder ranks them for the final selection. So, stage one is a graph-augmented encoder that retrieves candidates' articles by incorporating structural context into their representations. In stage one, we independently encode the query and each candidate articles using a bioencoder. To handle long articles, we adopt a hierarchical article encoder that segments the text, encodes each chunks, and aggregation the representations into the single embedding. The resulting article embedding are then enriched with the structural context using graph neural network. To incorporate structural context, we construct a legal structure graph from the civil code. Each node represents either an article or the structural headings, and edges reflect structural containment relationship, as I explained earlier. And we initialize each node's embedding using the bioencoder and then apply the graph neural network to propagate context across the graph. Both the encoder and the GNN are trained jointly. I'll describe the training process later. Next, I'll explain a bit more about how we construct the graph and how we perform GNN propagation. We construct a directed graph from the statutory structure by extracting structural units using regular expressions from the article text. The node includes statutory articles and structure units such as part, chapters, and captions. And the edges represent hierarchical containment like part, chapter, article. Citation references are not included as edges. Instead, we handle them by recursively inline the cited content into the citing article text. And legal articles often contain the explicit references to other provisions, such as in accordance with Article 542 or as defined in the preceding article. Rather than modeling these references as edges in the graph, we handle them by recursively inlining the cited content into the citing article. This choice helps avoid complexity in the graph structure and ensures stable input for the encoder. While we didn't model citation links as graph edges in this work, we consider that a promising direction for the future research. And to maintain a logical consistency and ensure a valid expansion order, we apply the topological sort to the citation dependency graph. So, first stage, we apply the graph neural network over the legal structure graph. Each node, such as an article and a structure heading, is initialized by the encoder and updated by the aggregated information from its neighbors using GATv2. Although the diagram shows GATv1, we still illustrates how attention works in the setting. So it will work, help. So the attention mechanism computes learned weights alpha for each neighbors, letting the model focus more on relevant nodes during propagation. This results in context-aware embedding that reflects both the node's content and its structure position. The equation summarizes the process as an attention-weighted aggregation with a nonlinear transformation. And next, in the second stage, we use a cross-encoder to rerank the top K candidate articles. For each of top K candidates retrieved in stage 1, we apply the cross-encoder to compute the scalar relevance score. The cross-encoder jointly encodes the query and the article, allowing it to capture fine-grained interaction between them. We then return only those articles whose score exceeds a threshold. Both the number of the ranked candidates and the threshold are tuned to maximize F2 on the development set. We use the pre-trained cross-encoder model named the Japanese Hierarchical cross-encoder LASV1, which provides solid performance out of the box. Next, I briefly explain how the biencoder and graph neural network are trained. Our training approach is based on contrastive learning, which encourages the model to distinguish relevant articles from irrelevant ones. We use contrastive learning to train both the encoder and the graph GNN-based retriever. The idea is to bring a relevant question-article pairs closer in the embedding space and push apart irrelevant ones. For each question, the gold standard articles form the positive pairs, and the unrelated articles are treated as negatives, either from the batch or retrieved by the baseline. This training helps the encoder learn semantically aligned representations and also provides effective initialization for the GNN propagation. And each question article pair is labeled as positive if the article is part of the gold standard answer set and negative otherwise. In addition to random negatives, we include hard negatives, articles that incorrect but look similar in wording or topic. These are obtained either through in-batch sampling or by retrieving similar articles using BM25. Including such example helps the model learn fine-grained semantic distinctions, which is essential for accurate retrieval in legal context. And we train the GLGR in 2 stages, both using contrastive learning with InfoNC loss. In phase 1, we pre-train the biencoder to distinguish relevant from the irrelevant articles using positive and hard negative pairs. In phase 2, we fine-tune the full model biencoder plus GNN on the same objective. The GNN propagates the contextual information across the graph, and its parameters are trained jointly with the base encoder. This setup allows the model to benefit from both semantic similarity and structure context. And for experiments, we use data from COLIEE Task 3. We report macro average F2 as a main evaluation metric, since recall is important in this task. As baselines, we compare against BM25 and biencoder model based on multilingual U5 base, evaluated in both its pre-trained form and after contrastive fine-tuning. GLGR also uses multilingual U5 base as the encoder backbone and evaluate it with and without cross-encoder reranking. And this slide shows the results on the development set and test set. The contrastivity trained by encoder outperformed the pre-trained version on both sets. JLGR without reranking gives higher recall, reflecting the effects of structural context via GNN. And reranking improves precision, likely due to the cross-encoder capturing finer interactions. We used general-purpose pre-trained cross-encoder without fine-tuning, so fine-tuning on legal data could be explored in future work. And our system, submitted as Team Info, ranked third out of 8 teams in the official evaluation. So we observed the GNN-based propagation improves recall even without relying on lexical overlap. Cross-encoder reranking improves precision by reducing false positives, though the model was not fine-tuned for the legal data. Our citation handling method is simple and effective, but it flattened the distinction between citing and cited content. In future work, we plan to explore modern citation links explicitly in the graph. So, to summarize, we propose JLGR, a structure-aware retrieval model for legal documents. It combines a bioencoder with a graph neural network for structure content propagation and uses a cross-encoder for ranking. Our results show that explicitly modern legal structure contributes to better retrieval performance. We believe this approach can be applied to other statutory domains as well. So thank you for your attention. I'm happy to take any question or feedback. Thank you. Mm-hmm. Mm-hmm. Sorry, is that question? Uh-huh. Also for encoding the text to it, right? You mean to create the graph or the to get the embedding, which does it? Okay, so I'll give you answer both. I use the multilingual E5 base, as I said, for creating the embedding, and then to create the graph, I use the regular expression, and yeah, I I defined the regular expressions, and I defined how to create a graph. So and then input the civil codes from the COLIEE 2025, and then it was made. Is that answer or no? Mm-hmm. Yeah. All right. Thank you. Yeah, I will consider that. Mm-hmm. Yeah. All right. Thank you. Yeah, I'm gonna consider that. Thank you very much.